Welcome back. In today's video, we want to find the current IA of t in the following circuit. As always, we want to convert any sinusoids into a positive cosine format to avoid confusion. So we can do that by using the trig identity. Cosine of x is equal to plus or minus sine of x plus or minus 90 degrees. Thus, our voltage source, Vs of t, is then equal to 40 times cosine of omega t minus 110 degrees. And that's in volts. We can then convert that into the phasor domain. And when we do that, we get a magnitude of 40 and an angle of 110. So the conversion is done using the relationship between the time domain and the phasor domain. Cosine of omega t plus theta can be converted over to the phasor domain. And whenever we convert, we get a, and we should have a in front of our cosine. And then over back in the phasor domain, we have a times the complex exponential e to the j theta, which can be written as a times the angle theta. So now that we convert our voltage source over into the phasor domain, we can then convert our capacitor and inductor. The resistor stay the same. So the impedance for the resistor stay the same. So the impedance of our capacitor is going to equal 1 over j omega c, or minus j times 1 over omega c. So we'll get minus j 25, and units are in ohms. And we do the same thing for our inductor. This time, the impedance of the inductor is equal to j omega L, which is equal to j 10 ohms. So, having convert our, and we're going to erase, just put a line through these. We're not using them anymore. So on our circuit, we crossed out the time domain, so now we're in the phasor domain. So now we can choose the method of analysis. And in this case, let's just use two methods. We're going to use node voltage and mesh current method. Let's start with node voltage. As you can see, I've already chosen node A and pre-drawn some currents. This one was already drawn, but basically what we're saying is that we're going to apply KCL at node A. So applying KCL at node A minus our voltage source all over the impedance for the capacitor, which is minus j 25 plus, and probably should, so that's A minus our voltage source all over the impedance of the capacitor, and it's A minus 0 volts divided by the impedance of the resistor, which is just A divided by 30 plus A minus 0 volts divided by the impedance of that branch. So that's A all over 10 plus j 10, and that is equal to 0. We can then go ahead and solve for the voltage at node A. So the voltage at node A, after we manipulate, we'll just probably just go through a little bit. So we factor out of A, we get 1 over 30 plus 1 over 10 plus J10 minus 1 over J25. And then we get a minus J times our source voltage, V of S, 1 over 25. So we can then say that A is equal to, J can be written as 1 with an angle of 90. So then we have 1 with an angle of 90 degrees times 1 over 25 is 0.04, and V of S is 40 times an angle of negative 110 degrees. And we then divide that by the expression, simplified expression. When we simplify that expression, we get 0.04, 0.84 minus 6.84. The voltage at A is then equal to 19.06 with an angle of negative 13.16 degrees. And that's in volts. So knowing the voltage at node A, we can then go ahead and divide that by the total impedance in that branch, and therefore get the current IA of T. So the phasor counterpart of the voltage of the current IA of T is equal to the voltage at node A, which is 19.06 divided by 13.16. All of that divided by the total impedance. So that's 10 plus J10. And in polar form, that is equal to 14.14 with an angle of 45. We then divide that, and we end up with 1.3479 with an angle of minus 58.15, and that's in degrees. Thus, we have our current in the phasor form. So if we convert over to the time domain, we then get IA of T is equal to 1.3, we can round that to 35, times cosine of omega t, which is 200 times t, and an angle of minus 58 or negative 58.15, or we can round that to 2. And that's in amperes. So the relationship, so to convert from the phasor domain to the time domain, we use back the same relationship we use when we convert to the phasor domain. And that's it for the node voltage method. We can go ahead and try the mesh current method. So let's now use the mesh current method to find the current IA of T. So if we go back here and we draw our mesh in the clockwise direction, we call that 1, and we call that 2. We can then go ahead and draft the two equations, which will be two unknowns, two equation, two unknown. So the first equation involve when we go around, that's a minus source voltage, a plus capacitance, or in this case impedance. So that would be a VFS minus VFS plus a I times the impedance of our capacitor, and then it'd be the difference between these two currents times the impedance of the resistor. So going around loop 1 clockwise, we encounter the voltage source, the minus terminal of the voltage source, plus, and this is I1 going around the loop with the impedance of the capacitance as minus J25 with a difference. So with a difference between I1 and I2 times the impedance of the resistor equals 0. Now if we apply, if we go ahead and apply same thing for the loop 2, we see that we'll have a difference between I2 and I1 times the impedance of the resistor in the middle, and then I2 times the impedance of this resistor, and then I2 again times the impedance of the 50 ohms, or and in this case the J15, the impedance of the inductor. So that is going to give us the difference. Let's start from the difference. So if we go ahead, and the difference between I2 and I1 times the impedance of the resistor, 30 ohms, plus I2 times 10 plus, so we're going to add, so we're not going to just, when we send I2 around, we're not going to send I2 around this, then we're just going to add the total impedance in that branch and then times that by I2. So that's going to be, the total impedance is going to be 10 plus J10, and that's going to equal to 0. Now we can rearrange our equations. So then if we move over our voltage source over to the right, we then get I1 is equal to 30 minus J25 plus I2 is equal to, in our case, negative, well, I2 is plus I2 times negative 30 ohms is equal to 40 with an angle of negative 110. For equation 2, I2 times negative 30 plus, and this should be I1, my bad, I2 times 40 plus J10 is equal to 0. So here we have two equations, two unknown, and solving will give the solution. And you can just set this up into your calculator or math lab or something. So we're going to do a simultaneous equation matrix. So in that matrix, we're going to have I1 as 30 minus J25. I2 is going to be a minus 30. I1 minus 30. I2 40 plus J10. And we have I1, I2 equal to 40 with an angle of negative 110 degrees and 0. So plug that into your calculator. You'll get a solution of I1 equaling to 1.852 with an angle of negative 44.1 degrees, and that's in amperes. I2 is then equal to 1.347 with an angle of negative 58.2, that's in degrees, and that's amperes. So based on our circuit, we know that I2 is equal to I A of t, or in this case just I of a. So we can then go ahead and transform I2. So let's write that here, that the phasor component I2 is equal to the phasor component I of a, and the phasor component I of a is the phasor counterpart for the time function I of at, and that is equal to 1.35 cosine, I think omega t was 200t, yep, omega t is 200t minus 58.2 degrees, and that's in amperes. So we can see that both method led to the same solution. However, one was, in a sense, fairly quicker. So if I was to solve this again, and I see that I have two loops, I'd go ahead with my mesh current method, because current is what I'm solving for. And the second method was, I think, the simplest or the easiest. So that's it for today's problem. I'll see you in the next one. Bye.